Hey guys, happy Monday. This is going to be our first little video to help us figure out how to do our NMR analysis. Pardon my voice, I'm sick and my voice is going, so this will be interesting. But anyway, we're going to start with a little basic molecule that you guys are used to counting the signals on. So let me just write this out. So we've done things like this in lecture already where you guys are used to figuring out how many signals would pop up on your NMR spectrum. So we're looking for unique groups of hydrogen. So in this one we would have two signals, right? Because we have one set of equivalent hydrogens right there. That CH3 is very unique all to itself, and that's different than the two hydrogens right here on these what we call the methylene hydrogens right there. So we're going to have two different signals. What we didn't get to cover yet in lecture is the splitting pattern of signals. So that has to do with how many equivalent neighbors a group of hydrogen has. So it's called the N+1 splitting rule. So let me write that down. The N+1 splitting rule, where N is the number of equivalent hydrogens. Hydrogen neighbors. And when we say neighbor, we're talking about who is exactly adjacent to a set of hydrogens. So, for example, if we were looking at the signal for this set of hydrogens, these three methyl hydrogens right here, notice right away, excuse me, that they are most shielded. They're the furthest away from the bromine. So looking at these hydrogens, I would say that they have two equivalent neighbors. Now, sometimes people get confused because they think, oh, you mean these are equivalent to these guys? And that's not what we mean. It just means that these two are the same to each other. So when I look at these hydrogens, I would want to think in my head, I'd say these hydrogens have two equivalent, I'm going to abbreviate that, and then neighbors, I'm going to abbreviate that too. So according to this rule, N+1, so since my N is 2, 2 plus 1 equals 3, we would then call the signal for these hydrogens a triplet. And we'll kind of draw a picture in just a minute of what that would look like. Okay, so again, these guys right here, they would have a triplet signal, and it would be, again, more upfield. A little more shielded than the other ones. Okay. Now, if we're looking at our second signal right here, well, we just have to look at our adjacent atom, which is the carbon, since the two carbons are bonded together, and this carbon has three equivalent hydrogens on it. So these hydrogens right here have three equivalent neighbors. Okay? So if I want to know what their signal is going to be split into, I add 1. 3 plus 1 is 4. This would be a quartet. Okay. So these guys right here, they have a quartet, and it would kind of be a little bit more downfield than our triplet here. Bromine's not extremely electronegative. If you look at your chemical shift chart, it's kind of somewhere, oh gosh, that whole halogen region, maybe around 3-4 parts per million, right in that middle section there. So I'm just going to say a little more downfield. And then your triplet. Okay, so what does a quartet and a triplet look like? So if we were to draw a little NMR spectrum right here, okay, we would have upfield, that alkyl region, you know, and it's anywhere from, gosh, like 0.75 parts per million to 1.5 parts per million, right around 1 parts per million. That's that whole alkyl area. Just kind of depends on how close you may be to another electronegative atom. But, you know, right around this 1 parts per million region, and again I'm saying approximately, so right around that area we would have a triplet. So a triplet looks something like this. Okay. Not beautiful, but again you kind of have this 1 to 3 to 1 ratio. Okay. And then a little bit more downfield, probably in that, I don't know, gosh, right around 3, and there's 4-ish down here, parts per million, approximately. There's a lot of stuff we looked at in that area. We would have our quartet. Now your quartet kind of looks like this. A 1 to 3 to 3 to 1 ratio, something like that. And then again, the relative heights kind of reflects the number of hydrogens. These hydrogens are pretty close to each other. They're just 1 difference apart there. So no huge difference in height there. But this is kind of something that you would see for the splitting pattern for this molecule right there. There's your 2 signals, and of course what the signals are split into. So we are going to analyze a bunch of the spectrums in our little lab right here. So I just want us to make sure we're comfortable with section 5 right here, counting how many neighbors we would have and what that would mean. So I'm not going to fill it in on this paper because I want you to do that, but let's just sort of talk it through. So number A, it says hydrogen atoms that report a singlet. So if you just saw a singlet, what does that mean? Okay, so a singlet would mean you have 0 neighbors. Okay, so hydrogen atoms that have a singlet for their signal would have 0 equivalent neighbors, because 0 plus 1 would give you the number 1, which is a singlet. B, we already saw a triplet. So a group of hydrogens, or maybe just this 1 hydrogen, to have a triplet, you have to have 2 equivalent neighbors. Okay, so a triplet, you have 2 equivalent neighbors. 2 plus 1 gives you 3. C, it says hydrogen atoms that report a multiplet. So something that's always going to be sort of hinted at you, and I always label it on a spectrums, are any multiplets. Now multiplets can be kind of messy looking signals. They're not clear at all. Sometimes they are pretty clear. You could count the number of peaks, but something that's really important is that you know that multiplets are telling you that the hydrogen that's giving that multiplet signal is because they have unequivalent neighbors. So I can show you a good example of what unequivalent neighbors would look like. So I'm going to draw that right here. So I'm going to do pretty much something similar to what we already did, but I'm going to add another CH2 group right there, and we'll keep it with bromine. Okay, so this time I have propyl bromide instead of ethyl bromide in the previous example. So this time, again, we would have 3 different signals. So we've got 1 signal there, really upfield, 2 signals there, and then hopefully you can recognize that these 2 hydrogens are different or unique than these 2, because remember, these 2 right here, they're right next to that bromine atom. This carbon is bonded directly to that bromine. This carbon is not. So we would have 3 signals. So if we want to know what they are splitting into, we have to look at our neighbors. So looking at these methyl hydrogens, these hydrogens have how many equivalent neighbors? So we look 1 atom over, and that carbon has 2 equivalent hydrogens. So we're going to say 2 equivalent neighbors. So 2 plus 1, again, we're seeing that triplet. That would be upfield in that 1-ish ppm region. Now we're going to switch all the way over to the right here. Now these two hydrogens that are a little bit more downfield, again in that whole, 2.5 to 4.5-ish parts per million region. Again, lots of things down there. If you look at your chart, we talked about things that are next to oxygen, next to nitrogen, next to halogens, all in that sort of 2 to 5-ish region there. So those ones that are a little bit more downfilled, if we count how many neighbors they have, we would say these hydrogens have 2 equivalent neighbors. So 2 plus 1 gives us 3. So we're having another triplet. Okay, so far we have 2 triplets here. Okay. Now those triplets are in different places. This is an upfield triplet. Okay. And this is our more downfield triplet. Again, maybe sort of the 3 to 4 parts per million region. Now, what about these 2 methylene hydrogens that are right there in the middle? Okay. Well, looking at these guys, we would say these hydrogens have, if you count your neighbors, we've got 2 hydrogens there, and we have 3 hydrogens there. But these 2 are different sets of hydrogens. They are not equivalent to each other. So we say these hydrogens have 5 unequivalent neighbors. So again, these are not the same types of hydrogen. So these guys have 5 unequivalent neighbors. So this is called a multiplet. Now, sometimes multiplets look very messy on a spectrum, or kind of depending on how many electronegative atoms are in that molecule, it helps the splitting become a little bit more clear. Now, bromine, again, is not that electronegative, but sometimes you can count the peaks, but I will always label if it's a multiplet or not. So sometimes you might see 5 plus 1 is 6. You'd see something that we call a sextet, but it's a multiplet. So if you hear that word multiplet, again, we just can't call it a sextet. That would mean 5 equivalent neighbors. A sextet multiplet is when a group of hydrogens has 5 unequivalent neighbors. So that's a really good example there of a multiplet. A multiplet, even if it's messy and you can't count the peaks, that's okay. Never get frustrated if you can't count things like this. Let me flip this over. If you can't count these peaks right here, that's okay. If it looks really messy and it's labeled multiplet, that simply tells you a lot of information, that those hydrogens have unequivalent neighbors. Okay, so going back down our little pre-lab here, D, hydrogen atoms that report a doublet. Well, a doublet means 2. So how do we get 2? 1 plus 1 would give us 2. So that would be 1 equivalent hydrogen neighbor. E, hydrogen atoms that report a sextet multiplet. Well, that's the one that we just went over. Those ones would have 5 unequivalent hydrogen neighbors, and we gave a good little example for that right there. So that is just your splitting pattern in a nutshell. What we're going to do in our next video, because I'm going to take a little pause because I'm losing my voice, we're going to start to analyze some real NMR spectrums. But something that's really important is that you make sure that your spectrum is analyzed. So to get credit in lab or a quiz or on exam, you have to prove you know exactly what that spectrum means. You can't just say, poof, have a structure on there and no one knows where that actually came from. So every NMR must be completely analyzed. So you need to have all of these things on there. Okay? So take a peek, read it over, and in your next video, we will start analyzing several spectrums in the NMR. All right, guys, signing out from my garage in the cold rain. I'll talk to you soon. Bye.